Okay, good day. This is Pre-Calculus. I am Mr. McCully. This is lesson 49 on evaluating limits. Let's get to it. Today we are going to use the dividing out technique to evaluate the limit of a function, and we are going to use the rationalization technique to evaluate the limit of a function. And I gotta say that while these are two very powerful ways to evaluate limits. They're not necessarily an exhaustive list of how you can evaluate limits. And we're just trying to get some simple introduction into evaluating limits before we get to calculus. So, main ideas. Many limits, and these are mostly limits that you'll see in calculus, cannot be evaluated through direct substitution, which we did a lot of in the last lesson. And again, just because a function is undefined at a point or is an indeterminate form does not mean that the limit also does not exist. So you can have an undefined and still have a limit, and that is hugely, hugely important, especially if you're going to move on to calculus. So we saw this one in the last video, so I'd like to address it again. And so we'll just pull up our graphing calculator, and we'll clear out that other fraction, and we'll go alpha y equals, and we'll go the fraction, and then it was x squared minus 4 over x minus 2. I think that's the one I had there. Oh, no, I didn't. Okay. Have it backwards. So let's clear this out. So we go to our graphic calculator, we hit alpha, we hit the y equals, we put up a fraction, and we have x minus 2 over x squared minus 4. Okay, so if I hit graph on this thing, we see that there is a non-removable discontinuity here at x equals negative 2, but there is no removable discontinuity at x equals to 2. But if I check the table here, and I go to both at negative 2 and positive 2, I get an error for both of those. And the reason that that is because when you plug in for negative 2 and positive 2 in for x, in both instances, we'll get 4 for the x squared, and when I subtract 4, I'll get 0. Now, when I plug in positive 2, I get 0 over 0, which again is an indeterminate form. Now, clearly, when I look at this function along the graph, at negative 2, if I come in from the left and I come in from the right, it looks like it's pointing at a value that we could determine. But because of the undefined, we can't make that determination based upon a direct substitution. So we got to do something a little bit different. And the way that we're going to do that for this particular one is we're going to use the dividing out technique. And it says that if two functions that are exactly the same for all but one or a few values must have the same limits for all values c in their domain. Thus, if a rational function has common factors, they can be divided out to find a new function with the same limits. This only applies to the limits of the two functions, not necessarily all the values, because again, we're going to get some values in the new function that are defined where they aren't in the old function. So let's look back at this. And we're going to try the dividing out technique. And so the first thing we want to do when we're using the dividing, D-I-V-I-D-I-N-G, out technique, all right, is we're going to factor. So I'm going to rewrite this. I haven't taken the limit yet, so I want to keep writing the limit until I actually evaluate the limit. So I've got x minus 2, and this is a difference of squares. So I get x minus 2, x plus 2. And so here we're going to cancel. And we want to note we are creating a new function that is similar to the old function. So what I'm going to do here is I am going to cancel out this factor x minus 2 and my new function as x goes to 2. When I cancel those out, I'm going to get 1 over x plus 2. Now this particular function is going to look almost exactly the same as the original function with the exception of x equals 2. So if I come down to this second function in the red and I go y equals, and I hit alpha, y equals, hit 1, and we go 1 over x plus 2, and I hit graph, we notice that I get essentially the same thing. They look exactly the same, but the only difference is when I bring up my table, at x equals positive 2 in the original, just have to enter. There we go. In x equals 2 in the original, I get an error, but when x equals 2 in the new function, I get 1/4. All right, so here's what I've done. Just as a review, this function and this function are not the same functions, but because this new function has every value that this function has with the exception of when x equals 2, I can say that the limits for these two functions must be the same. And since I can do a direct substitution in this second function, I can go 1 over 2 plus 2 and say that this limit is 1/4, and this function also has 1/4 for that limit. And we saw that fairly clearly. The other technique that we want to talk about is the rationalization technique. If a function is undefined or an indeterminate point, another method that can be used to evaluate the limit is to rationalize the numerator or denominator to make an equivalent function that is not undefined or indeterminate form at that. So let's look at an example like that. So if I were to plug in 0 for x, I get a 0 on the bottom, that would make it undefined, and then I have square root of 2 minus square root of 2, and that would be 0 on the top. So this thing is an indeterminate form. And so we are going to use the rationalization technique, rationalization technique. All right, so we're going to use the rationalization technique, and we're going to multiply by a funky 1, right, to get rational values in the numerator. All right, so we're gonna, again, we aren't evaluating the limit yet, so we got to leave the limit notation in there, and that's a big error that kids make. They leave that limit notation off, so make sure you keep entering your limit notation until you evaluate the limit, and hopefully I'll remember to bring that up when we get there. So it's x plus 2 minus square root of 2 over x. And so I'm going to multiply by the square root of x plus 2. Instead of minus, we're going to do a conjugate, plus square root of 2 over the square root of x plus 2 plus 2. And so this is a minus b times a plus b is a squared plus b squared. And so again, haven't evaluated the limit yet, so I have to write it. The limit as x goes to 0. And so this thing becomes the square root of x plus 2 squared. So the square root and the square cancels out, and I get x plus 2. And then this becomes square root of 2 squared, or just 2, all over x times, and you're gonna see why, but I'm not gonna distribute just yet. Square root of x plus 2 plus square root of 2. Then the limit, again, I haven't evaluated yet. As x goes to 0, I get x plus 2 minus 2 is just x. And then I have an x on the bottom with that square root of x plus 2 plus square root of 2. And you'll notice that the x's cancel out, so they divide out there, and I get the limit as x goes to 0 of 1 over square root of x plus 2 plus square root of 2. And you'll notice here that when I let x go to 0, it's no longer undefined. I get a 0 there. So I get 1 over the square root of 2 plus the square root of 2. Notice I haven't write the limit. I'm not writing the limit anymore because I'm actually evaluating this limit. And I get 1 over 2 square root of 2. Now we shouldn't leave the square root in the denominator. So we'll multiply by square root of 2 over square root of 2. That'll give me square root of 2 over, I'll have 2 times square root of 2 quantity squared, which is just 2. So 2 times 2 is 4. And that is my final answer. All right there, folks, that's all I've got. So, the Star Wars fun fact of the day: in Star Wars Empire Strikes Back, C-3PO claims that the odds of successfully navigating an asteroid field is approximately 3,720 to 1. And that number we should find very suspicious, because when you're thinking about odds, it's basically saying that if you were to travel through an asteroid field 3,721 times, you would expect to successfully do it once, which translates down to about 0.27%. That's pretty oddly specific, considering that if you got a big ship, you might run into more asteroids if the asteroid field had not very many asteroids in it. So I would suggest that that's a fairly suspicious number and just made up. But what do I know? I'm just a math teacher. That's all I got, folks. Have a good day.